switching gears a little bit away from sort of acids and bases that I'm like, oh, I'm making some solution in the lab, and I want to buffer, HCl. That's not quite as practical in the body. So what we want to talk about now is what differences in pH do to actual macromolecules. So what were our biological macromolecules that we've talked about before? There's like 3 to pick from, maybe. They're like the titles of chapters 1, 2, and 4. Yes. Lipids. Lipids actually were the only one that were not a macromolecule in the sense that they don't polymerize into like a nice long chain, such as proteins or DNA, right? So the bases were like our monomers making a long chain of DNA, or our amino acids were like the monomers making a long chain into a polymer. Glycans could make a long carbohydrate. Lipids were the only one that were a little bit different. They are one of our important biological molecules, but they had like a polar group and tails. They don't behave in sort of these long chain structures. Okay. So this is like a mini version of a protein here. Okay. We have the N-terminus. We have our amine group over here, and then we have a carboxyl group on the C-terminus over here, and in between we write this protein chain as, say, alanine, threonine, glycine, alanine, whatever these are. Okay, so we can just write our string of amino acids in our protein. Normally we think of the N and C termini as having charge on them, and depending on the pH of the solution that this protein is in, whether or not a hydrogen is on either side of these. So if you were to put a hydrogen on here, this would no longer have a negative charge. If you were to take one off of your amine group, it's no longer positively charged. So sort of the N groups could be protonated, meaning it has a hydrogen on, or deprotonated, depending on pH of the solution. The same thing is true for any given one of the amino acids. Now, most of ours were uncharged, but we did have some that were permanently charged. And when you vary pH, at some point you may put on or take off a proton to some of these charged groups. Okay. So changes in the side chain charge would have profound consequences on the protein's function, because function is dictated by folding, and folding depends on some of these key interactions. And so if you have 2 charged groups that need to get together and interact through some sort of ionic non-covalent interaction, a salt bridge or whatever, let's say, if they do not have the proper protonation on that side group, they're not going to be able to make the interaction you expect. Folding doesn't pan out. Okay? So the effect is going to be greatest for side chains that have a pKa value very near to cellular pH. So if you have a pKa value very close to 7, you're at risk of actually having your proton kind of hop on and hop off and have some effects. If you are always, if your pKa value is very far from cellular pH, it's not expected that you'll be really affected at all. Okay? So here are the pKa values of some side chain groups. We have the C-terminus, the carboxyl group here, has a pKa of about 3. We have cysteine, tyrosine, lysine, arginine. So again, we have a bunch of pKa values. These pKa values given here in this table, 10.11, represent if you could isolate just that amino acid and put it in water. So these are sort of theoretical values. They're not real life. Okay? But if you could have isolated amino acids in water, this is what you would expect the pKa of each of these things to be. Okay? And so we're going to talk about histidine, because the His group has a pKa of about 6. And so what we have here, on the left side of this sort of reaction, we have our protonated form. Okay? So it has a hydrogen group attached to this nitrogen here. This is our protonated form, or we consider this our acidic form. And then as we go forward in this reaction, the proton is hopping off. So this would be like a conjugate base form plus a proton. You might also call this the deprotonated form, however you want to think of that. Okay? So the pKa of histidine is about 6, meaning that at a pH of 6, there would be equal amounts of charged and uncharged side chains. Okay? If I was at a pH of 6, I would expect to find half of my histidine residues with a proton on and half of them without their proton on. Okay? And that's illustrated here. It has a pKa of about 6. If I'm at a pH of 6, when I subtract this over, 6 minus 6 is 0. The only way to get a log of this to be 0 is for this ratio to be 1. So it means I expect to have about equal concentrations of my, like I said, acid kind of form and conjugate base form. And the way this is just written here, and you'll probably see on practice problems and homework problems, is the acid is on the bottom. It has the little plus sign representing that the proton is there. And then the top just does not, rather than having it as sort of A minus for the conjugate base, it now has nothing there. The proton is off. So acidic and basic form. Okay. If we were to shift the pH unit in either direction, the ratio of deprotonated to protonated histidines will change by a factor of 10. So this is a property of this log base 10. So at a pH of 5, okay, 5 minus 6 gives me a negative 1. So a negative log is because this ratio is less than 1. Okay, so I would have this ratio of deprotonated to protonated histidine residues is 0.1. So another way to think about this is for every 10 residues that I have, 9 of them have the proton on, and 1 of them doesn't. That's a way to think about it. At pH 7, it goes the other way. Okay? The other way that's sort of helpful for me to think about this is intuitively when pH drops, I have a higher concentration of protons around. If they're around, they'll get onto histidine and raise that concentration. So again, lower pH means I have more protons. pH is the concentration of H plus that's hanging out. I don't know where it came from, but it's there. And if it's there, it'll join up with histidine and protonate it, so this bottom term gets bigger and this ratio gets smaller. Okay? And vice versa if pH goes up.